Hi, we're going to finish up chapter 3. So we're going to talk about why quantum mechanics helps us understand chemistry better and how the periodic table is based on our understanding of quantum mechanics. So I'll share my screen. Okay, so we left off here with a beginning discussion. Get all this stuff out of the way. A discussion of how electron configurations relate to the periodic table. So your periodic table has rows and it has columns, and a row is called a period and a column is called a group. So the periodic table arranges atoms so that elements with the same chemical and physical properties are in the same group. And it's interesting that the periodic table was developed by Mendeleev, and it was developed before we understood anything about quantum mechanics. So he looked at the chemistry of the elements and how some had similar properties and was able to put them into the periodic table that way. And so once quantum mechanics was developed, it just helped us understand why those were the arrangements for the elements. So elements in the same group, so that's a column, have similar valence electron configurations. So remember, the valence electrons are the electrons outside of a full inert gas. So the last group in the periodic table are the noble gases, and their electron configurations are super stable. So if you have electrons beyond that, those are the electrons that give elements their properties. So valence electrons play the most important role in chemical reactions. That's just what I said. And this describes why elements in the same groups have similar chemical reactivity. The reactivity is similar because they have similar valence electrons. So transition elements or transition metals are metallic elements in which the last electron is added to a d orbital. So that's that middle part of the periodic table. And the valence electrons, those added after the last noble gas configuration, they could include s and they can include d electrons. So vanadium is an example where you fill argon, and then you go over and you'll have 2 electrons going into s orbitals and then 3 into d orbitals. So inner transition elements are those metallic elements in which the last electron added goes into an f orbital. So the f orbitals are being filled when you're in those bottom 2 rows that are below the periodic table. And they're only down there because the periodic table would be too wide if we inserted them where they belong. So it's easy to see where they insert based on how the atomic number of the elements change. So the valence electrons here added after the last noble gas include the s electrons, and then whatever the s n quantum number was, it'll be n minus 2 for the f. And there might be some d electrons or d subshell, and that would be n minus 1 for the d. So this is just an example. And we will do a lot of these in class, so we'll just look at how you do them. So if you're talking about ions, an anion is something that's negatively charged, so you added an electron to it. So the added electrons are added in the order that would be predicted by the Aufbau principle. So they go into the lowest energy that's not occupied first. So predicting electron configurations of ions. So for a cation, you're going to take electrons off, and for an anion, you're going to add some. So if you want to write the electron configuration for the parent atom, and then add or remove the appropriate number of electrons. So if we look at sodium, it starts out at 1s2, 2s2, 2p6, 3s1. And if it loses 1 electron, it has lost that 3s electron on the outer. That was its valence electron. If you notice, this is actually the electron configuration of neon. So if we wrote it abbreviated, it would help us understand why sodium likes to be +1. Phosphorus, so if you write the electron configuration, its outer electrons are 3s2, 3p3. And to become a an anion, it will pick up 3 electrons, so it will fill that outer 3s orbital, or 3p orbitals, sorry, the set of 3p's. Each of those will pair up, and now it'll be a 3p6. So aluminum starts out with a 3s2, 3p1 valence shell, becomes a +2, so it's going to lose the p electron, and then one of the 3s electrons. Iron is in its valence a 4s2, 3d6. The other are inner shell. So when it loses 2 electrons, they're removed from the 4s orbital first. So that's one of the rules for the D series. And you can't really do the calculations right now. It takes calculus. And if you take an upper level course, you could actually calculate the energy of the orbitals, and you could understand why when you fill them, the S's are lower in energy, but when you start taking them away, you're not also taking away protons. And so the energy of those orbitals shifts a little bit, and the S orbitals are actually higher in energy than the D. And so for a F2 plus cation, you're going to take the electrons out of the highest energy location, which is the S. SM, if it's going to become a +3, so it starts out with the outer electrons as 6s2, 4f6. So when it loses 3, it's going to lose 2 from the s orbital, and then it's going to lose 1 from the f orbital. So it will become 5p6, 4f5. So it's lost those 6s2 electrons and one of the electrons that's in the 4f. So now if we think about what we know about how electron configurations relate to the periodic table, we can think about trends in the periodic table, properties that different groups have in common. So we're going to be able to describe and explain the observed trends in atomic size, ionization energy, and electron affinity in the groups. So a lot of properties of elements vary periodically. So it might be that as you're going from the left to the right of the periodic table, the size of the elements are getting smaller. And if you go down a period, it's also true if you go from the left to the right. So they're going to have properties that vary periodically as the electronic structure of the elements change. So these properties govern the chemical behavior of elements. So these include the size of atoms and ions, the ionization energies, and the electron affinities. So the radius is actually, because you can't really say exactly how big an atom is, because it goes forever, but you can look at a covalent bond. And if you look at a covalent bond, you can define the radius that way. So if you have 2 atoms bonded together, and if you cut it 1/2 the distance, then you're going to say that that's the size of the nuclei that was in that bond. So as we look down a group, the principal quantum number increases by 1 for each element, and the electrons are added to a region of space that's increasingly further from the nucleus. So as n gets bigger, the probability of where you find the electron gets further from the nucleus. Therefore, the size of the atom gets bigger. So the size of the atom and its covalent radius increases down a group for that reason. But as you're going from left to right, even though you're adding more electrons, something called this effective nuclear charge is increasing. So that's the pull exerted on a specific electron by the nucleus, taking into account electron repulsions. So as you add electrons, each time how much the previous electrons shielded you from the nucleus will determine what the the effective nuclear charge is. So for hydrogen, there's only 1 electron, and so the nuclear charge Z and the effective nuclear charge are equal, because there aren't any other electrons influencing how much of that positive nuclear charge that electron sees. But for all other atoms, the electron of interest are partially shielded from the pull of the nucleus by the other electrons present. This is so much better done in class. So we'll talk it through, but like a lot of things, hopefully in class, you'll ask questions and I'll go through this and make it more visual. So core electrons are adept at shielding, while electrons in the same valence shell don't block the nuclear charge experienced by each other as effectively. So if you think about it, if you have electrons in a shell and you try to put an electron out here, the electron out here is shielded from that positive charge by all of those electrons that stand in its way. But if you have electrons in this shell and you try to put another electron in this region, it's not shielded from the nucleus by the other electrons as much. So it's going to be held tighter and it's going to be smaller. So each time we move from one element to the next across the period, so going from left to right, Z increases by 1, but the shielding increases only slightly due to the electrons being added to the valence shell. And so Z effective increases as we move from left to right across the period. And so with the stronger pull, higher effective nuclear charge is experienced by the outer electrons and it draws them closer to the nucleus. Therefore, the size of the atom and its covalent radius decreases from left to right. So as you're going down a group, the atomic number is getting bigger and you're getting more electrons and the atom gets bigger. But because the Z effective gets bigger going from left to right, atoms actually get smaller as they have more electrons in a period. So this just gives you a visual of the relative sizes. So if you look going from lithium over to fluorine, you can see that noticeable decrease in size, or from cesium over to AT, you can also see that visual decrease in size, whereas as you're going down a group, so as you're going down from hydrogen, let's say, to francesium, I think that's what that's called, they're clearly all getting bigger. So with each period, the trend in atomic radius decreases as Z effective increases. For example, from potassium to krypton, within each group, the trend is that atomic radii increases as Z increases. So this shows you that trend. So from lithium down to neon, they're shrinking because you're going from left to right. But then when you go from lithium to sodium to potassium, you'd be going down a group, and so they're all getting bigger. So when you look at ionic radii, it's slightly different. So the ionic radius is the measure used to describe the size of an ion. And a cation always has fewer electrons than the same number of protons as the parent atom. And so as electrons are removed from the outer valence shell, the remaining electrons experience a greater Z effective charge and are drawn even closer to the nucleus. A cation is always smaller than the atom from which it is derived. An anion is different, though, in that it always has more electrons than the same number of protons and the same number of protons as the parent atom. And this results in a greater repulsion among the electrons and a decrease in Z effective. So the charge on the nucleus doesn't feel as strong because of those other electrons being added. And this causes the valence electrons to be further from the nucleus. And an anion, therefore, is always larger than the atom from which it was derived. So this is just a couple of visuals to show you that. Aluminum and the +3 cation, sulfur and the -2 cation. So if things are isoelectronic, so isoelectronic just means atoms and ions that have the same electron configuration. And so examples are given here. So if you look at these on the periodic table and look at the anions with added electrons and the cations with electrons taken away, in that first row, they all end up having the electron configuration of neon. So atoms or ions that are isoelectronic, the number of protons determine the size. So if you have more protons, the nucleus has a greater charge. And if you have a greater charge on the nucleus, but the same number of electrons, then you're going to have a smaller radius if you're looking at a series of isoelectronic ions and atoms. So another property of atoms and ions that has a periodic trend in the table is the ionization energy. So the ionization energy is the amount of energy required to remove the most loosely bound electron from a gaseous atom in its ground state. That's called the ionization energy. So the most loosely bound would be the highest energy electron. So if we have X in the gas phase and we pull an electron off, we call that the ionization energy number 1. So IE1. You can also remove a second electron. And so the second ionization energy would be to start with your cation where you've already taken off an electron and remove a second one. So that second equation represents, if you had an ionization energy number 2, that would be the energy for that process. Take an electron off of an already positively charged cation and make it a +2 cation. So the energy required to remove the third electron is the third ionization energy, and you could go on and on. So energy is always required to remove electrons from atoms and ions. So ionization processes are endothermic, and ionization energies are always positive. So you think, like when you think about something like sodium, sodium exists almost 100% as Na+, as a +1 cation, but that doesn't mean its electrons just fall off. They come off because they're interacting with something else that has enough energy to pull those electrons off. So as size, atomic radius increases, the ionization energy decreases, which makes sense because if an electron is further from the nucleus, if the atomic radius is bigger, then it's not experiencing that charge on the nucleus as much. It's further away, and so it's going to be easier to pull an electron off. So the first ionization energy decrease down a group and increase going across a period, because we know that that's how the periodic trend is for radius. It gets bigger going down and it gets smaller going left to right. There are a few deviations from this trend based on electron configurations, but that's the general trend. So when you look at this, these are some of the deviations. So hydrogen to helium gets harder, lithium to neon gets harder. But for example, going from nitrogen to oxygen, if you think about it, we'll look at this in class because it's hard for me to show you. It seems, well, yeah, if we look at this, it'll make more sense. So when you look at this, like going from nitrogen to oxygen, why doesn't it just get harder to pull off an electron? Well, when you look at it, if you look at nitrogen, it has 2p3. So it has 3 individual p orbitals, each with 1 electron. So taking off an electron will be taking it out of a p orbital that just has that 1 electron in it. But when you get to oxygen, one of its p orbitals has the electron paired. And so it's going to be easier to take that off because the electron, so it's harder to take it off because oxygen is smaller, but it's easier to take it off because the electrons repel each other. And so that repulsion of 2 electrons in the same orbital makes it slightly easier to pull that off. So you can think there'll be a similar trend if you look at each of these going across a period. Beryllium, so let's look. So from beryllium to boron, why is that a trend that's not the same? So going from beryllium to boron, boron should just get harder, but it gets slightly easier. And so the electron removed during the ionization of beryllium is an s electron. The electron removed during the ionization of boron. So if you look at boron, its outer electron is a p electron, whereas beryllium, it's an s electron. And so the electron removed during the ionization of boron is a p electron, and the energy of a subshell increases as L increases. This means that an s electron is harder to remove from an atom than a p electron in the same shell. So just because it's in a different L subshell, it makes the boron slightly easier. This is explaining the trend I just talked about with nitrogen, that if nitrogen and oxygen, that if you're removing one from oxygen, It eliminates that electron-electron repulsion caused by pairing the electrons in the 2p orbital. So the electron you're taking out of an oxygen atom is this one that's in a paired p orbital. And so this means that removing that electron from oxygen is more energetically favorable than removing one from nitrogen, where it's just coming out of a p orbital that only has one electron. Removing an electron from a cation is more difficult than removing an electron from a neutral atom because of the greater pull. So anytime the nucleus anytime the species becomes positive, then it's going to be progressively harder and harder as it becomes more positive to pull an electron off. So removing an electron from a cation with a higher positive charge is more difficult than removing an electron from an ion with a lower charge. So that means that if you talk about first ionization energy relative to second to third, the third is always higher than the second, and the second's always higher than the first. So successive ionization energies for an element always increase. It's always harder to take an electron off the more positively charged the species is that you're leaving behind. So this is just a table giving you some ionization energies. And you'll notice, and we'll talk about this in class, that for something like potassium, the first ionization energy is 418.8 kilojoules per mole, and the second one is 3051.8. So there's a huge jump going from 1 to 2. But the jump going from 1 to 2 is based on, if you look back, so let's look at potassium. So for potassium, the first electron that comes out, so element, it doesn't actually give the atomic numbers there. So for potassium, when you take the first electron off, you end up back at neon's electron configuration. So that's relatively easy. But then for the second ionization energy, you'd be taking an electron out of neon's completely full shell, and that's much, much harder. That's why you have that huge jump going from the first ionization energy to the second. So at some point, there's always a large increase in successive ionization energies for an element. So I talked about potassium. This large increase corresponds to the removal of core electrons, which are harder to remove than the valence electrons. So for example, if we look at scantium and gallium, they both have 3 valence electrons. The large increase in ionization energy occurs after the third ionization energy. So let's look at that. Yeah. After the third. Yeah, you can see that going from the second to the third isn't that big of a difference, but then going from the third to the fourth, that's where you have a huge difference, a huge jump in ionization energy. So this large increase occurs after the third ionization energy because you would have taken off the 3 valence electrons, and then to take off the fourth one, you'd have to be digging into that inner shell. So the last property we're going to talk about is called the electron affinity. Similar to the ionization energy, but not exactly the same. So the electron affinity, EA, is the energy change for the process of adding an electron to a gaseous atom to form an anion. So you start with a neutral gaseous atom, you stick an electron on, and you get a negatively charged anion. This process can either be endo or exothermic, so it depends on the element. Ionization energies were always positive. You always had to put energy in. It was always endothermic. But with an electron affinity, it's a little bit different. Sometimes it's a process that happens, and sometimes you can't get it to happen. So for some elements, energy is released when the gaseous atom accepts an electron, and for others, it's required for the gaseous atom to accept an electron. So it can either have a negative or a positive electron affinity. So it becomes easier to add an electron as the effective nuclear charge of the atoms increase. So that makes sense. If you want to stick an electron onto an atom, it's going to be easiest to do if it sees a large effective nuclear charge. So electron affinities become more negative going from left to right. So as you go from left to right, atoms shrink. Therefore, the effective nuclear charge gets bigger, and therefore it will be easier to stick an electron on. And as always, there are some deviations in this trend. So the deviations really come about because it's really a playoff. So if you think about it, to stick an electron on, if it sees a high effective nuclear charge, that makes it easier. But then, for example, if you're putting that electron into an orbital that already has an electron in it, there's some electron-electron repulsion, making it harder for it to stick on. So depending on who wins, essentially, that will determine whether or not it's a favorable process or not a favorable process, where you get energy out or you put energy in. So for the noble gases, which have a completely filled shell, the incoming electron must be added to a higher energy N value. So it must be added to a new shell. And group 2 has a filled NS subshell. And so the next electron added has to go into the higher L value, which is a P subshell. And group 15 has a half-filled P subshell. And the next electron must be paired up with another electron. So that's what I was just talking about. So in all of these cases, the initial relative stability of the electron configuration disrupts the trend in the electron affinity. So if we look at this, gives us the electron affinities. So so the ones that are positive are the ones that are least favorable. The ones that are negative give you the most energy out. So if you look at it, if you look at group 17, they all have very high negative electron affinities because they're going to take a almost full shell and make it full. Whereas when you look at the noble gases, almost all of them have positive electron affinities, meaning electron doesn't want to stick because it's going into that new shell. Neon, it does have a negative electron affinity. I did not know that about neon, and that's interesting. But because neon is so small, its effective nuclear charge is greater than, example, if you go down to argon and krypton. So the periodic table, we want to state the periodic law and explain the organization of the elements, predict the general properties based on their location, identify metals, nonmetals, and metalloids. So a lot of this is general descriptive chemistry, which I would never ask you on a test, but it helps you to start thinking about the properties. So I've mentioned Mendeleev. He is the most famous one for creating the periodic table. I did not know that someone named Meyer also independently recognized that there was a periodic relationship between the properties of the elements. And so the periodic table was created in 1869 and 1870. Quantum mechanics wasn't completely developed until 1926. So they're doing all of this before we knew anything about orbitals. So this is the descriptive kind of chemistry that I wouldn't ask you about, but group 1 and 2 are metals, so that makes them shiny, conduct heat and electricity well. Those are just things that it will, as you go on, you'll get more familiar with. So the first periodic table with the elements were arranged according to the increasing atomic mass. And Mendeleev used his table to predict the existence of elements that would have properties similar. So where there were holes in the periodic table, so where there was should be an element with a greater mass with a property similar to the one above it, they later discovered those elements that he knew were missing. So at this time, we didn't even know of the existence of all the elements. So the discoveries of gallium and germanium provided basically holes, or provided elements to go into the holes that Mendeleev knew existed. So we didn't know about all of the elements at the time, 1969. So these didn't get discovered until 75 and 86. So that made Mendeleev's work really significant, that he was able to predict elements that we would discover. So this is just a picture of his early periodic table and a picture of him. So the modern periodic table, it becomes apparent that the periodic relationships involved atomic numbers rather than atomic masses. Because we know the atomic mass can be bigger because it might be a heavier isotope. So it's really the charge on the nucleus that creates these periodic trends and not that mass. So the periodic law is that the properties of the elements are periodic functions of their atomic numbers, not their atomic masses. So a modern periodic table arranges the elements in increasing order of their atomic numbers and group numbers with similar properties in the same vertical column. So a group is a column, and all of those elements have similar properties. So periods or series, those are the horizontal lines. We've already talked about that. Groups are the columns. That's just showing you that those two elements would have similar properties. So metals are shiny, malleable, good conductors of heat and electricity. Malleable means that you can shape them into different shapes, so you can easily not bend them, but easily shape them, I guess is the word I will use. Non-metals are dull, poor conductors of heat and electricity, and metalloids conduct heat and electricity moderately well and possess some properties of metals and some properties of non-metals. So main group elements, 1, 2, 13, 18. Transition metals are groups 3 through 13. We'll look at the periodic table. We should really have this on a slide with the periodic table. And the inner transition metals are those bottom two rows. So we have alkali metals, group 1, except hydrogen, alkali earth metals, group 2. I've never even heard that word for group 15, 16, 17, the halogens, but I've never even heard the other two, and I'm a chemist. So a lot of the descriptive words for the periodic table we won't focus on. So this is just showing you what it told us. You have the alkali metals, the alkali earth metals, group 1 and 2. The transition metals, you're filling D electrons in that middle region. You have the lanthanides, the actinides. Those are the F series at the bottom. Okay, I think we can keep going here. Let me see. We'll keep going. Oh, no, I think I'll take a break. I feel like this is a whole new idea. So now we're going to talk about bonding in different kinds of molecules. So this is a very, very, very long chapter. So I think I'll take another short break and we'll do this